ইকুয়েশনের দ্বারা দিস ফ্যাক্ট তাহলে ম্যাগনেটিক ফিল্ড আমাদের আমরা সবথেকে ভালো দেখতে পাই নর্থ এবং সাউথ পোলে। যখন কিনা সূর্য থেকে সিএমএসি থেকে নির্গত ইলেকট্রিক প্লাজমা পৃথিবীর ইলেকট্রিক ফিল্ড থেকে রিফ্লেক্ট হয় এবং তাই এনার্জি নর্থ এবং সাউথ পোলে ডাইভার্ট হয়ে অরোরা ক্রিয়েট করে, যেটি দেখতে চমৎকার লেগে থাকে লাইক দিস ইমেজ। ইম্পর্টেন্স, এটি আমাদের জীবনে কি কি কাজে লাগে? কম্পাস নেভিগেশন, শিল্ড অ্যাটমসফিয়ার, হেলথ, স্যাটেলাইট এন্ড এভিয়েশন এন্ড অ্যানিমাল মাইগ্রেশন। সামারি, যে আর্থ ম্যাগনেটিক ফিল্ড যেটি হয়ে থাকে আউটার কোরে, সেটির মাধ্যমে জেনারেট ইন দা আউটার কোর এসেনশিয়াল ফর লাইফ, যেটি আমি দেখলাম আগেরটাতে যে আমাদের অ্যানিমালস মাইগ্রেশনে কাজে লেগে থাকে, এবং ডাইনামিক and continuously charged. Thank you.
প্রিন্স রয়কেও তার টপিক আর্থ ম্যাগনেটিক ফিল্ড আমাদের সামনে পরিবেশন করার জন্য ধন্যবাদ জানাই। ইতিমধ্যে আমাদের সামনে তিনটে টপিক আমাদের 6 সেমিস্টারের স্টুডেন্টরা পরিবেশন করেছে। সায়নের লাইট টপিক নিয়ে, রণদীপের সেমিকন্ডাক্টর নিয়ে এবং প্রিন্সের আর্থ ম্যাগনেটিক ফিল্ড নিয়ে, এবং যথেষ্টই প্রশংসার দাবিদার জানায়। এরপর আমাদের মাঝখানে আমাদের সায়ন্তিকা বোস তার ফোননিক ক্রিস্টাল টপিক পরিবেশনের জন্য মঞ্চে আহ্বান জানাচ্ছি।
Good afternoon. Today my topic is wave mechanics, the solid state framework of phononic crystal and acoustic metamaterials. So, introduction and core physics concepts. Today in this topic we are diving deep into the classical wave mechanics of engineering structure known as phononic crystals. While it is historically difficult to pinpoint the exact origin of acoustic metamaterials, phononic crystals were part of the first architecture to manifest truly acoustic phenomena. At its core, the foundational physics is defined by a beautiful mechanism. Phononic crystals are periodic composite materials that allows acoustic waves to travel through specific frequency ranges known as passband, while completely inhibiting wave propagation across other frequency through an acoustic band gap, enabling absolute control and manipulation of phonemes. They allow us to realize exotic dispersion characteristic because the sound wave propagation is often completely unattainable in naturally occurring chemically constant materials. Instead of relying on atomic properties or natural molecular bonds, these structures consist almost entirely of carefully assembled artificial inclusions embedded in a host matrix, which act as macroscopic wave scatterers. As documented in the literature, like physics or sound ideas, band gaps are universal wave phenomena observed across three distinct physical domains: electron wave in semiconductors, electromagnetic wave in photonic crystals, and mechanical wave in phononic crystals. So this is the picture. Actually, this is the diamond known structure. And it is written here, periodic structure can block sound waves in certain frequency ranges and direction when interference effect lead to the formation of phononic band gaps. And phononic properties of 3D crystal are diagonal symmetry, as it is shown here. Like this artificial 3D structure are currently being investigated. So these phononic crystals have, they are made in such a way that only few frequency of wave can pass through them. And if the frequency is matched, then the wave is passed through them. And if the frequency is not matched, then they collide against this this type of structure, and they broke into the species, another small waves, and they neutralize all the waves. Thus, only certain type of frequencies can pass through these crystals. I think all you know that how to make tea, and this structure, phononic structure, are like the ships. Ships mean, if I tell in Bengali, this is called the cha chapti, or it is called chapti. And it is made out of some wires, and if we pour the tea on the ships, we can see that the water or the tea pass through it, only the tea leaves, which are blocked by the ships. So actually this structure blocks the certain type of frequencies, by frequencies. And this is phononic crystals use is that suppose someone is talking in front of me, or I have to block that sound. So phononic crystals help us to for that. Even they can block the high frequency of jet sound. So what is metamaterial and their physics-based types? To understand the fundamental physics, we must position phononic crystal within the broader classification of metamaterials. Metamaterials are artificially engineered composite structures designed to exhibit unique exotic properties that are often completely unattainable in naturally or chemically conceived materials. Instead of relying solely on the chemical composition of the atom, their macro properties are dictated by geometry, arrangement, and size of the engineered internal building blocks or inclusions. Actually, the metamaterial shows such kind of properties that is called exotic properties. If we make some crystals or some materials in a chemical way, they will not show such properties. So this is the beauty of the metamaterials. In physics, metamaterials are categorized by the fundamental 12 equations they manipulate. Electromagnetic or photonic metamaterials, these govern light and radiation by artificial manipulating Maxwell equation through engineered local variation in electrical permittivity E and magnetic permittivity mu. Acoustic or mechanical metamaterials, these govern elastic and acoustic wave equations by modifying the effective mass density rho and the elastic tensor component. So my topic is phononic crystal, and phononic crystal is type of a part of acoustic metamaterials. And other type of metamaterial is thermal metamaterials. And this manipulate the heat equation to dynamically govern conduction and redirect thermal flux. So this is the picture. I have chose it from a research paper, and here it is written that influences on the material properties of the metamaterial. You can see there certain speciality of this intrinsic size effect, inherent material properties, architecture, and intrinsic size effect microstructure. So yes, this is type of metamaterial is listed here: electromagnetic metamaterial, mechanical metamaterial, acoustic metamaterial, and you can see about each type. And with the electromagnetic metamaterial, we can build advanced optical devices. With the mechanical metamaterials, we can devise advanced structural and shape-shifting properties. And the acoustic metamaterial, as I said before, it can be made the silent acoustic materials. And it is written here that they sound and they control the sound and the vibration. The continuum physics connection, phononic crystal versus metamaterial. What separates a standard phononic crystal from an acoustic metamaterial? It is a question of operating regimes and wavelengths. First, phononic crystals serve as historical and physical foundation for acoustic metamaterial. The distinction between them comes down to a strict wave filtering transition criterion based on the relationship between the wavelength and the lattice periodicity. The Bragg region, that is lambda, is almost equal to a standard phononic crystal blocks sound through a Bragg rule bandgap, which relies heavy on the destructive interface from geometric diffusion when the sound wavelength is on the same order as the lattice spacing. The metamaterial sound regime. It is when the lambda is more greater than compared to the A. When another condition is also satisfied, where the global thickness of the crystal satisfying a multiple of 4 or 5 where T greater than A, the crystal exhibits hybridization bandgap at much longer subwavelength region where lambda is much greater than equal to A. And the subsequent research efforts studying these architectural characteristics have led to the proliferation of the acoustic metamaterials that exhibit a range of novel functionalities. So this is the diagram. This is same I have chosen from a research paper, and it is written that showing types of phononic crystal and associated frequency with vector relationship. And this is the picture of their wave vector versus this graph. And B, C, and D shows the indication of the phonon dispersion from experimental, theoretical, and numerical model as available. So there are 3 types of model. This is the experimental model, this is the theoretical model, and this is the numerical model. And you can find the image. It is written adapted from this journal. And you can see that their structure is 3 types of model is almost same. Little bit difference there is between them. Then my topic is structure of phononic crystal. How phononic crystals are structured? A phononic crystal is structurally defined as an artificially structured periodic composite made from 2 or more elastic phases with highly contrasting mechanical properties. From a structural physics perspective, the infrastructure, it consists almost entirely of carefully assembled inclusion embedded within a host matrix material, the mechanism. These inclusions act as physical microscopic wave scatterers. As I said before, these phononic crystal uses wave scatterers. They break and scatter the wave, and then waves, small waves, nullify and create and then nullify all the waves. So we cannot hear the unnecessary sound. It consists almost entirely of carefully assembled inclusion embedded within a host matrix material. The mechanism, this inclusion acts as physical macroscopic wave scatterers. This material periodicity introduces a macroscopic crystal lattice that forces the classical mechanics wave to conform to the underlying symmetry of the system, creating an acoustic analog to an atomic grid. So this is the phononic crystal structure. This is the A. This is the picture A. It is written as symmetric representation of an light emitter embedded in a phononic crystal slab of hexagonal lattice with periodic parameter A and thickness D is equals to 0.25 A. This is the detail about the D structure. And B, it is the top view of the phononic crystal slab. The yellow region is a P. Region represents a dielectric media with the E gap is equals to eta gap is equals to 10.5625, and the white region shows air holes. This is the air holes. This is the white region. And there are other structure you can read from this box. Is written in the number C. This is the C, and this is D, and this is E. And it is the electric field amplitude for the passband mode of K1. This is K for K1 and this is for K2. And the vectors K1 and K2 in the irreducible Brillouin zones are shown as green arrows in D. So, as I mentioned earlier, that is to destruct the unnecessary waves. And so, phononic crystals are materials that allow acoustic wave travel to specific frequency ranges known as passband, while inhibiting other frequencies through a band gap, thus enabling precise control and manipulation of tones and sound. This is the light frequency radio wave, and this is the high frequency radio wave, and this is the low frequency radio waves. This is the definition of this frequency. Dimensional classification of phononic crystal. Phononic crystals are categorized by the dimension for their physical periodicity, and there are three types of their dimension. This is the 1D, this is the 2D, and this is the 3D. And this is the copyright for VDCH. And what is 1D phononic crystal? The mechanical properties vary periodicity in only one spectral direction, such as alternating parallel reals or 1D laminate stacks for two different materials. This is the two-dimensional phononic crystal. The mechanical properties vary periodically along two spatial axes like Gauss matrix embedded with an array of parallel cylinders, pillars, or holes. You can see this is a kind of parallel cylinders. And there is the three-dimensional phononic crystal. These material properties vary periodically along all the spatial axes such as PRs or complex lattices and in a 3D matrix. And there is a topological thing of this 3D structure, that is complex topological architecture is crucial here, and the branch structure can be customized to the use of filing ratios featuring materials with very elastic constant. For 3D configuration, it is so that face-centered cubic or the FCC lattice architecture are far more favorable, generating full absolute band gaps compared to the body-centered cubic BCC geometries. This is the mathematical framework mapping onto solid-state physics, and as I mentioned in the topic name, so I connected with the solid-state physics with the mathematical things. And you can see this is the lattice point, this is crystal structure, single crystal, polycrystal, and these are crystal planes. And these are laws of solid physics, this is band theory of solids or Bloch's theorem. And this is lattice point notation. Cubic unit cell, simple cubic, body-centered cubic, face-centered cubic. And these are unit cell for different type of axes, system and angles. This is Bragg's law, as this phononic crystal follows kind of Bragg's law. And then is physics-driven material properties. The physical properties of the structure provide unprecedented tunability over acoustic fields, acoustic impedance constant. A full band gap is optimized by featuring components considering mass, densities, and contrasted Sonic velocities in a Morse matrix. Maximizing this contrast widens the result band gap significantly. Lattice gate invariance. Unlike quantum electronic crystals, classical wave mechanics is scale invariant. We can create a band gap at practically any frequency or wavelength we choose by simply scaling the physical size of the unit cell. If you want to blow hypersonic waves, you engineer sub-wavelength nanometer features. If you want to see audible or structural vibration, we can scale the lattice to centimeter or meters. And this is the picture of band structure. And see. This is written about the physical driven material properties like acoustic band gaps, negative reflection, acoustic clocking. And acoustic clocking that phononic crystals are used in bending sound waves perfectly around an object like submarine. And this type of things. This is the double negative metamaterial, and one of the most notable characteristic of phononic crystal was regarding the Bragg band gap, which is closely related to the band diffraction. This means sound wavelength and the lattice periodicity A become comparatively close, establishing lambda is almost equal to A when another condition is satisfied when the global thickness T of the crystal satisfied multiple of 4 or 5 at T greater than is more greater than A. The crystal shows hybridization band gap as lambda is more greater than A, leading to exotic phenomena such as negative mass density and elastic modulus. This is also negative. That is, it is called the double negative metamaterial. Where such characteristics are being demonstrated, a phononic crystal satisfies the criteria of acoustic metamaterial. In case of material, there are two types of materials. If we apply pressure on it, there shows a force on a hand. Like suppose I have creating force on a material and it shows and it oppositely create a force in my hand. But this type of metamaterial, if I force and apply force on the material, it seeks more. And this is the negative mass density and the negative elastic modulus. This is the properties. So the applications of phononic crystals is written. Advanced engineering application and conclusion. By controlling the underlying dispersion curve through solid-state framework, we unlock application that completely bypass natural acoustic concept. Today, phononic crystal exhibits huge potential for a wide range of novel functionalities like acoustic insulation and filtering, waveguides and wave showing, collimation and beaming, imaging and shockproofing, or acoustic cloaking. You can see there are properties: noise control and filtering, negative reflection, wave manipulation, acoustic image and testing, protective systems, and advanced concept of cloaking. And these are the references of my topic. So, in conclusion, phononic crystal is the macro world of the structural engineering with the micro world of solid-state physics. The two black concepts like block waves, backscattering, and the Brillouin zones are not unique quirks of subatomic electrons but universal laws of wave physics. By tailoring structural lattices rather than chemical bonds, we achieve arbitrary strain control over the acoustic environment. Thank you very much for it.
সায়ন্তিকা বোসকে তার টপিক ফোননিক ক্রিস্টাল পরিবেশন করার জন্য ধন্যবাদ জানাই এবং তার জন্য শুভেচ্ছাও জানাই। এই টপিক পরিবেশনের মাধ্যমে অর্থাৎ স্টুডেন্ট সেমিনারের মাধ্যমে যে শুধু সে বিষয়টি সম্বন্ধে বা একজন সুবক্তা হিসাবে নিজেকে প্রতিষ্ঠা করতে পারলো শুধু তাই নয়, ভবিষ্যতে উচ্চশিক্ষায় তাদের এই সেমিনার পদ্ধতিতে তারা আরো ভালোভাবে সাফল্য পাবে, এটা একটা তাদের বেস হিসাবে ধরে নেওয়া যেতেই পারে। এরপর আরেকটি ইন্টারেস্টিং টপিক ব্ল্যাক হোল পরিবেশন করবে স্নেহা শীল। তাকে মঞ্চে আসার জন্য আমন্ত্রণ জানাই।
Hello everyone, I'm Sneha Shil from the Department of Physics, and today I would like to take you on a journey into one of the most interesting topics in our universe, black holes. Imagine an object that is so powerful that nothing can escape from it, not even light. Such an objects are called the black holes. Although black holes may sound like a science fiction, but they are real objects that exist in our universe. In fact, scientists have even photographed them. The idea of black hole became possible because of the work of Sir Albert Einstein and his theory of relativity. In his special theory of relativity, Einstein showed that time is not absolute and can change depending on motion. Later, in general theory of relativity, he proposed that gravity can bend space and time itself. We can imagine space-time as a stretchable rubber sheet. When a massive object is placed on it, the sheet bends. The greater the mass, the greater the curvature, and the stronger the gravitational pull. This leads to an interesting question. What would happen if an object becomes so massive and dense that the gravity becomes unbelievably strong? The answer is a black hole. But how are black holes formed? To understand this, we first need to understand the life of a star. A star remains stable because two forces are in balance. Gravity continuously pulls matter inward, while nuclear fusion inside the core produces only a theoretical prediction because they emit no light. They became the greatest achievement in the modern astronomy. In 2019, scientists released the first ever image of black hole, that is named M87, using the Event Horizon Telescope. And in 2022, scientists achieved another milestone by releasing the first image of Sagittarius A. This is a supermassive black hole that is at the center of our own Milky Way galaxy. One of the most popular questions in our physics is, what would happen if someone falls into the black hole? According to our current understanding, the gravitational pull on your feet will be much stronger than your head. The enormous difference in gravity will stage your body into a long, thin shape. Scientists call this process spaghetti fusion. What happens after crossing the event horizon still remains a greatest mystery in our modern physics. Black holes continue to challenge our understanding in space, gravity, time, and the universe itself. Even more than a century of research, many questions remain unanswered, and perhaps the next great discovery is still waiting to be made. Thank you.
স্নেহাশীলকে তার টপিক ব্ল্যাক হোল পরিবেশন করার জন্য ধন্যবাদ জানাই। তো ইতিমধ্যে আমাদের মধ্যে 5 জন অসাধারণ সেমিনার প্রদর্শন করেছে, প্রত্যেককেই তাদের টপিক পরিবেশন করার জন্য শুভেচ্ছা জানাচ্ছি এবং তাদের জন্য আরো একবার সবাইকে অনুরোধ জানাবো, একবার জোরে হাততালি হয়ে যাবে। তাদের এর পরবর্তী সেমিনার আশা করব আরো অডিয়েন্সের সঙ্গে কানেক্ট হোক, সেই আশা রেখেই এবং তারা এত স্বল্প সময়ে এটা প্রস্তুত নিয়েছে তার জন্য ধন্যবাদ জানিয়ে আজকে সেমিনারের এখানেই আমরা সমাপ্তি ঘোষণা করছি।